Good morning. Can you hear me?
Yes.
All right, thanks. Okay, so today we're going to talk about the Euclidean algorithm. So the Euclidean algorithm is used to find out the greatest common divisor of two integers. Although we have the definition of the greatest common divisors of two integers, but we do not have a good way in our hand to find it out. So before we study the algorithm, let's first talk about a few lemmas. So the first lemma says that if a is a positive integer, then the greatest common divisor of a and 0 is a. All right, so this is clear because any integer is a divisor of 0. And for a, the greatest divisor is a itself. So this lemma is trivial. Okay. And the second lemma says that if a is a positive integer, then the greatest common divisor of a with itself is a. Okay, so this is always also trivial. So we don't need to prove it because it's clear. Because the greatest common divisor of a is less than or equal to a, and a is a greatest common divisor. So the next lemma is the key lemma for the Euclidean algorithm, which says that if you have two positive integers, say a greater than b greater than 0, and in this situation, we can write by the remainder theorem, a can be written as b times q plus r, where r is the remainder. Then what we can claim is the greatest common divisor of a and b is equal to the greatest common divisor of b and r. Okay, so let's first look at the statement of the lemma. So you have a greater than b, and when you write a as bq plus r, remember the r is strictly less than b. Of course, because a is greater than b, so r would be less than a. So the lemma tells us the greatest common divisor of a and b is equal to the greatest common divisor of b and r. In other words, we reduce the largest number a to the remainder r. So you make it smaller. Okay, so this lemma tells us we can always use this lemma to reduce the larger number here to the remainder. And of course, we can repeat this lemma one more time. Since r is less than b, then we can also write b as a multiple of r plus the new remainder. You can do this repeatedly, then you eventually reduce these two numbers to much smaller numbers, which you can observe the greatest common divisor directly. Okay, so this is how you use this lemma to find out the greatest common divisor. Let's prove it. So what we're going to show is that the set of common divisors of A and B is just the set of common divisors of B and R. Once we show these two sets are equal, the maximum is are the same. Okay. So proof. So we'll show that the set of common divisors, remember, CAB means the set of, okay, so this is the set of common divisors of A and B. Okay, let me put a parenthesis here, is equal to the set of common divisors of B and R. So once we show these two sets are equal, then the maximum, which is the greatest common divisors, are the same. Okay, so to prove two sets are equal, recall the strategies. We first show one set is a subset of the other and show the other set is a subset of the original set. So first, we prove C of AB is containing C of BR. Okay. To show this, well, we take an arbitrary element in C of AB. Let D belongs to C of AB. So D is a common divisor of A and B. Then this means D divides A and D divides B. Okay, now since A is equal to BQ plus R, so we can rewrite R to be A minus BQ. So remember a linear combination. So R is equal to A minus BQ, which is a linear combination of A and B. In particular, this implies the common divisor D divides R. So D divides R. Now, since D also divides B, hence D belongs to the common divisor of B and R. All right. So this is the one direction. C of AB is a subset of C of BR. So next, we are going to prove C of BR is a subset of C of AB. So let's start a new page. So next, we show that C of BR is a subset of C of AB. To show this, we take an arbitrary element. So let D be in C of BR. Then this means D divides B and D divides R. So again, since we know that A is equal to BQ plus R, so this means A is a linear combination of B and R. We get D divides A, okay? So we have D belongs to the common divisor, a set of common divisors of B, A and B. Okay, because D is a divisor of B, now D is a divisor of A. So therefore, we have C of AB is equal to C of BR. Hence, the greatest common divisor of AB is equal to the greatest common divisor of BR. Okay, so this finishes the proof. Okay, now let's talk about the Euclidean algorithm. So the Euclidean algorithm uses the previous lemma repeatedly to find the greatest common divisor of two integers a and b. All right, so let's look at an example. So let's look at an example.
Can you go back real quick?
Yeah.
I'm just going to take a picture of it. Okay, thank you.
Mm-hmm. Okay, so let's look at an example. How to compute the greatest common divisor of, say, 803 with 154. Okay, so you should first remember here our A is equal to 803, B is equal to 154, okay? So in order to apply the lemma, A is 803, B is 154. So how to compute the greatest common divisor? So the step one is what you write is you write 803 as by the remainder theorem. So this is equal to 154 times what? So you can see this is 5, I think. And by a simple arithmetics, so what you get is this is plus 33. Okay, so this is arithmetics. So you have to remember to make sure this remainder, well, is less than b. Okay, the remainder theorem requires the remainder is less than b. Okay, so this implies what? By the remainder theorem, by the just now the lemma. The lemma tells us the greatest common divisor of 803, 154 is equal to the greatest common divisor of 154, 33. Okay, you can see B is the same, but we put the remainder, we use the remainder 33 to replace the larger number A, 803. So this is the first lemma. So you can see we actually go from here to a smaller pair of numbers. And then, of course, we can use the lemma again to reduce one more time. So you can, now this time you should remember 154 is a larger number, is A in the lemma, and the 33 is B in the lemma. So you are going to write 154. This is equal to 33 times, okay, so 4 plus 22. So this, by the lemma, would tell us the greatest common divisor of 154, 33 is equal to the greatest common divisor of 33. We're going to replace the larger number 154 by the remainder, which is 22. Okay, so while you may claim that you already see the greatest common divisor, but let's do one more time to make it even simpler. So next, we write 33 as 22 times 1 plus 11. So this implies the greatest common divisor of 33, 22. This is equal to the greatest common divisor, 11. And we can do one more time. So 22 is equal to 11 times 2 plus 0. So this implies the greatest common divisor of 22, 11, is equal to the greatest common divisor of 11, and the remainder, 0. But then by the lemma, we proved that the greatest common divisor of positive number with 0 is equal to what? It's just equal to the number itself, 11. So now from this procedure, so this eventually tells us the greatest common divisor of 803, 154 is just equal to 11. Okay, so you can see the Euclidean algorithm just uses the lemma repeatedly. Each time you reduce the larger number to the remainder, and you keep using the lemma, you reduce one more time to the remainder. Eventually, you are going to reach this step. Okay, so one number is a positive number, the other is going to be 0. So once you reduce it to this situation, then you are done. Okay. So any questions about this Euclidean algorithm? Because this is an important algorithm which will be certainly tested.
So question, that's the work you want us to show, and the scratch work is to get the greatest common denominator, we do the scratch work on another sheet of paper.
Yeah. For this kind of arithmetics, for example, you can do this on the scratch paper. You don't need to show me the work, but you just write down what you get. But these procedures you need to show. So you see, so all those work you need to show, because this tells me that how you use the Euclidean algorithm to get the greatest common divisor. So this part, the left-hand side, you just write down the things like that. Okay, you of course when you get the remainder, you need to work on a scratch paper how to write it in this form. But the right-hand side tells me you understand the Euclidean algorithm.
Gotcha. Thanks.
Okay. All right. So let me give you another example, and I'll give you 3 minutes to work by yourself. Then I'm gonna talk about solution. So compute the greatest common divisor of 1028 and 642. Okay. So please work for 3 minutes. Okay, so let's stop here, and I'm going to tackle. You just check whether you get the correct solution. Okay, so what we do is still the same. So here we first write the larger number, as a multiple of the smaller number plus a remainder. So this is 642, of course, times 1. It's clear. So what is the remainder? This is going to be, so 6 is a large digit, and 8 and 3. Okay, so this implies the greatest common divisor of 1028 and 642. This is equal to the greatest common divisor of 642 and 386. Okay, and then next, let's write 642 is equal to 386. So still we have to multiply a 1 and plus, okay, so you do a subtraction. So what you get is 6, 5, and 2. Okay, so this implies the greatest common divisor of 642 and 386. This is equal to the greatest common divisor of 386, 256. All right, and then we write 386 as a multiple of 256 times 1. So this is equal to, what's the remainder? So it's 0 over 3, 130. This implies the greatest common divisor of 386, 256 is equal to the greatest common divisor of 256 and 130. And let's keep doing this. 156 is equal to 130 times 1. So this is 126. So this implies the greatest common divisor of 256, 130 is equal to the greatest common divisor of 130, 126. And then 130 is equal to 126 times 1 plus 4. So this implies the greatest common divisor of 130, 126 is the greatest common divisor of 126 is 4. Okay, and now 126 is equal to 4 times 31 plus 2. So this implies the greatest common divisor of 126, 4 is just the greatest common divisor of 4 and 2. Let's do one more time. So 4 is equal to 2 times 2 plus 0. This implies the greatest common divisor of 4 and 2 is equal to the greatest common divisor of 2 and 0. And the greatest common divisor of 2, 0 by the lemma is equal to 2. This implies the greatest common divisor of the original pair of numbers is just 2. Okay, so you can see the Euclidean algorithm, once you understand it, what's remaining is just arithmetics. So you just need to do this computations repeatedly until you reach 0 as one of the numbers. Okay, so so this is the Euclidean algorithm. So another application of the Euclidean algorithm is that once you write this use this Euclidean algorithm to find out the greatest common divisor of two numbers. So you are able to write the greatest common divisor as a linear combination of the two numbers, because we have a theorem which says that the greatest common divisor of any two integers can be written as a linear combination of these two integers. But at that time, the method we used is only to try to find out the linear combination without a very clear strategy. We just try to check whether we can make it. But now, once we have the Euclidean algorithm, we have a procedure to write the greatest common divisor as a linear combination of the two numbers. So here, let's look at the first example here. So let's try to write the greatest common divisor of 803 and 154 as a linear combination of 803 and 154. So in other words, what we want is this one. So example. So write the greatest common divisor of 803 and 154 as a linear combination of 803 and 154. So you can see it's not so easy for this example. If you don't have the Euclidean algorithm, it's not so easy to find out what is the linear combination to make an 11. Okay, now what we are going to do is the following. So we start backward from your procedure of the Euclidean algorithm. So look at here. So you first find out the first place where 11 appears as a remainder, because the greatest common divisor is 11. So let's check. So this step, the remainder is 0. And you go one step up. So here you do get a 11 as the remainder. So once we find out this step, so 11 is a remainder, you can start from here. So this step tells you what 11. So let's solution. So this is 11 is equal to what? 33 minus 22 times 1. Okay, this is what you get from the step where 11 appears as a remainder. Okay, now the next step is you go one step up. So when you go one step up from here to here, now 22 is a remainder. So you are going to replace 22 as a linear combination of 154 and 33. So here we're going to replace this 22. So this is 33 minus, okay, now 22 is replaced by 154 minus 33 times 4. Okay, because you have a multiple times 1. Don't forget this times 1, because sometimes this is not 1. So you, okay, so this is just to replace, this parenthesis is to replace 22. Now we need to simplify this representation. So this is 33 minus how many 33? So don't compute. What you are doing is to just keep those numbers like 33, 154. You just write it. This is as 33 times 5 in this case minus 154. Okay, so don't multiply out those numbers. You just need to keep those factors 33, 154 and combine those terms which contain 33 or 154. It's clear you have a 33 here. You have 4 times 33. So what you get is 33 times 5 minus 154. Okay, Now you need to go one step up. So this time you go from here to here. Now 33 is the remainder. So in this representation, you are going to replace 33 by a linear combination of 803 and 154. So what you get is in this, the last step is 803 minus 154 times 5. Okay, this is to replace this 33. So you have a multiply 5. Don't forget about multiply 5. And minus 154. Okay. So the parentheses replace 33. Okay. Now you do one last computation. So this is 803 times 5. And if you look at negative 154, this is multiply 25 and minus 1. This is minus 154 times 26. All right, so remember a linear combination is in the form of addition. So what we get, this is equal to 803 times 5 plus 154 times negative 26. So here the coefficient is 5 and negative 26. So this is a linear combination. You see, we start from 11. We find the first place where we get 11 as a remainder. And then you replace 11 by a linear combination of these two numbers. And then you go one step up to replace a smaller number by a linear combination of two larger numbers. And you keep going up. Each time you replace the smaller number by a linear combination of the larger numbers, then eventually you get a linear combination of the two largest numbers. So to write the greatest common divisor of two integers as a linear combination of these two integers, you first have to follow the Euclidean algorithm to find out the greatest common divisor. Then you go backward to write the greatest common divisor as a linear combination of the two numbers. So any questions about this procedure? Okay, so okay, so if you don't have questions, let's proceed to the next topic. So this is a fundamental theorem of arithmetic. So this theorem is fundamental theorem of arithmetic. So the theorem says that every number greater than 1 factors into a product of primes that is M is equal to P1 times P2 times PS. Further, writing the primes in increasing order, P1 less than or equal to P2 less than or equal to PS makes the factorization unique. Okay, so the fundamental theorem of arithmetic just tells you any integer greater than 1 has a prime factorization. And in this factorization, if you put them in increasing order, then the factorization is unique. Of course, in this factorization, some of the primes could be equal, because if you look at this restriction, P1 could be equal to P2. It could happen all these PIs are all equal. Okay, maybe some of them are equal, maybe all of them are equal, maybe none of them are equal. Okay, but in any case, you have a prime factorization. So for example, so if you look at 600, so if we write it as 2 times 300, and then you factor another 2 times 150, you factor another 2 is 75. And then you can see we can factor 3 is 25. And then you get a 5 times 5. Okay, so this one is, of course, P1, P2, P3, P4, P5, P6. Of course, this is in increasing order, so this factorization is unique. Okay, factorization is unique. So this is exactly what the fundamental theorem of arithmetic says. Okay, so before we prove the fundamental theorem of arithmetic, we need 2 lemmas. Okay, so the first lemma tells us that a prime number divides the product of 2 integers, then the prime number should divide one of these components. So the first lemma says that if P is a prime number, it's a prime, and P divides A times B, then P divides A, or P divides B. Okay, so let's see how we prove it. So assume that P divides A times B. Okay, if P divides A, then we are done. Okay, so we only need to focus on the case when P does not divide A. So if P does not divide A, so this notation means does not divide A, okay? I put a bar on this divided notation. This means, okay, let me see, P does not divide A. Okay. Well, let D be the greatest common divisor of P and A. Okay, so since P is a prime number, so the divisor of P is just 1 and P itself. So since P is prime, P has only 2 positive divisors. One and P. So in this case, because D is a greatest common divisor of P and A, so in particular D is a divisor of P. So there are only 2 possibilities. Then D equals to 1 or D equals to P. But since we are already assumed, since P does not divide A, we have the greatest common divisor, then D has to be 1, okay? Because D is the greatest common divisor of P and A. In particular, D divides A. But we know that the P does not divide A, so D cannot be P, so D has to be 1. So D is equal to 1. This means the greatest common divisor of P and A is equal to 1. And since P divides A times B, remember previously we proved the lemma. If some number divides a product and this number is co-prime with one of the numbers, then this number has to divide the other number. So recall, okay? Recall the lemma, which says that if, say, something D divides A times B, and D and A are co-prime, then D divides B. So in this situation, we already showed that the greatest common divisor of P and A is 1, which means P and A are co-prime. Then we get P divides B. Okay. So you can see if P is a prime, either P divides A So in the case when P does not divide A, then P has to divide B. Okay, so this is a good lemma for prime numbers. Actually, this lemma can be generalized to the product of n numbers. So this is the next lemma, which is a generalization of this lemma. Okay, so the next lemma generalizes the previous lemma. So let P be prime if P divides A1 times A2 times you have n numbers an, then P divides AI for at least one I in the set 1, 2, n. So if P, a prime number P divides a product of n numbers, then P must divide at least one of those numbers. So this is what the lemma says. This lemma is actually a generalization of the previous lemma. So we can prove by induction. Okay, let's review the procedure we've learned in the beginning. Proof by induction. So okay, step 1. For n equals to 1, then we have P divides just A1. So in this situation, we are good, okay? Because this is exactly, you only have one number. A1, of course, it divides it. Okay, step 1 is trivial. Step 2, assume for n equals to n0, the statement is true. So you should understand what this means. The statement is true. It means if P divides the product of n0 many numbers, then P at least divides one of them. Okay. Now for n equals to n0 plus 1, and let P divides A1 times A2 times an, an0 times an0 plus 1. Okay, so we want to show P divides at least one of them. So how to prove this? So what we are going to do is we're going to regroup it to a different product. Then P divides now, the first one is A1 and A2, and an0 minus 1. And the last two numbers, we group them together. an0 times an0 plus 1. Okay, so now we treat this as the product of n numbers. This is the first number, the second number, the n0 plus 1's number. The last one is the n0's number. So P divides the product of n0 numbers, so by hypothesis, okay, by our assumption. So here, this is the assumption step. This is the assumption. we have P divides a I between 1, in this case is 2 and 0 minus 1, or P, okay, let me write it rigorously. For some I belongs to 1, 2, up to n0 minus 1, or P divides the last number, which is a n0, times a n0 plus 1. Okay, because we are treating this as a set of n0 numbers. So the assumption says that if P divides the product of n0 numbers, P must divide one of them. Okay, so if P divides AI for some I belongs to 1, 2, up to n0 minus 1, then we are done. Because this already fits our statement. So if P divides a n0 times a n0 plus 1, now this step we need to use our previous lemma, because our previous lemma showed that if P divides the product of two numbers, then P has to divide one of them. So by previous lemma, P divides a n0, or P divides a n0 plus 1. So combine all of this, therefore, P divides a I for some I in 1, 2, up to n0 plus 1. Okay, so at this point, we are done. So you just use the previous lemma to combine with the mathematical induction to show the lemma here. Okay, so now we're going to use this lemma to show first part of the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic says that any integer greater than 1 has a prime factorization. And moreover, if you rearrange those prime factors in increasing order, then the factorization is unique. So let's first prove the existence that is there exists a prime factorization. So here we talk about the proof of the fundamental theorem of arithmetic This is for the existence. So we want to show there exists a prime factorization. After we show the existence, then we show the uniqueness. So if you rearrange the factors in increasing order, then the factorization is unique. Okay, so how to prove the existence? We are going to use the lemma, previous lemma. So let's first make it clear that what is the statement of the existence. So the statement is if n is greater than 1, then there exists primes P1 up to PS where S is greater than or equal to 1. Such that n is equal to P1 times P2 times PS and P1 less than or equal to P2 less than or equal to PS. So this is what we want to prove, okay? All right, again, we'll prove this one by mathematical induction. Okay. So step 1. Since n is greater than 1, so the initial step is n equal to 2. And this is clear since 2 is prime. So n equals to 2 is already the prime factorization, okay? So step 2, assume for n for n greater than or equal to 2, less than or equal to k, the statement is true. Okay, so here, if you look at this assumption, this is a variation of the mathematical induction. So the standard form of the mathematical induction is you just assume for n equals to, okay, let me put n0 for consistency. Okay, so the standard form of the mathematical induction is to assume for n equals to n0, the statement is true. Now the variation is you can assume for n less than or equal to n0, or the statement is true. So this gives you a little bit more freedom. But essentially, this is the same because you are always go from steps to step. Okay. Now for n equals to n0 plus 1, So if n0 plus 1 is prime, then we are done. Because in this case, n is just a prime, so it's of course a prime factorization. And if n0 plus 1 is not prime, so recall the theorem we proved that any composite number, because n0 plus 1 now is composite, any composite number can be written as a product of two numbers, and these two numbers are both less than the original number. Then by our earlier lemma, so we know that n0 plus 1 is the product of A and B with both A greater than 1 less than n0 plus 1 and B greater than 1 less than n0 plus 1. So in particular, this means A is between 2 and n0, and B is between 2 and n0. Okay, now we can use our assumption here. Our assumption here is for all the numbers between 2 and n0, you always have a prime factorization. So by assumption, so we can write A as a product of P1 times P2 times Pk, and B is equal to Q1 times Q2 times Qs. Therefore, you have n0 plus 1, because n0 plus 1 is A times B, is P1 times P2 times Pk times Q1, Q2, Qs. So we get a prime factorization of n0 plus 1. And of course, you can rearrange this. It is clear that we can rearrange those primes in increasing order. In increasing order. Okay, so this finished the proof of the existence. So you can see that by first decompose n0 plus 1 as the product of two numbers greater than 2, then use the assumption each component A or B can be written as a product of prime numbers. Then you get the final conclusion, n0 plus 1 is the product of primes. So the order is just easy because this is a product of finite many primes. You can always rearrange it in ascending order. Okay, so this is a proof of the fundamental theorem of arithmetic. And since the proof of the existence requires a little bit more efforts, so we're not going to prove the existence, the uniqueness. I'm sorry, since the proof of the uniqueness requires more efforts, so we don't have time to prove it today. So we'll prove it next time. So, but one thing I want to say is that next Thursday, this Thursday, just 2 days, the day after tomorrow, we are going to have a review for our third exam. The third exam will be on next Thursday. Okay, so I'm going to send an email to tell you the exact details for the arrangement. Okay, since do you have any questions? Okay, so if you don't have any questions, so we are going to stop here today. And please look at the examples for the Euclidean algorithm and how to write the greatest common divisor as a linear combination of the two integers. So those two things are very important, which are going to be tested. So you must know how to use the Euclidean algorithm and the reverse procedure to solve some problems. All right, if you don't have questions, then we're going to stop here today. Bye-bye.